Hello, this is Sam, and in this video I'm going to give you a really brief overview of how the code for my Connect 4 robot works. So this is the main file here, main.py. This is the file in which the main game engine is run. I used a text-based Connect 4 game code from a guy named Keith. And I built my project basically on top of his Connect 4 game code that had kind of a pre-built AI in it that uses the Minimax algorithm, which basically is an algorithm that looks a certain number of turns into the future, and then makes the best decision um, based off of all this information. Um, so really basically how the code works, we start by creating a blank board, um, and right now we have that the turn is going to start with the bot is going to move first. Oh, I should mention the whole game is played on a 6x7 array of 0, 1s, and 2s. It's kind of like how how the board is represented. So 0 is an empty spot, or on my board it's green since I put a green piece of paper behind the boards, so that just to make the color detection algorithm easier. And then a 2 is a blue piece, which is the bot piece, and a 1 is a red piece, which is the human player piece. So we start. Let's just say it's the human player's turn. What this function here does, get board, it waits until until a new piece is added to the board, and then once a piece is added to the board, then it moves on to the bot turn, and the bot uses the Minimax algorithm to determine the best column to put in a piece, and then once they figure out that spot, then they will drop a piece. The bot will drop a piece in that column. This is using kind of a linear actuator. I have a stepper motor on kind of a really big like worm screw in which the piece dropper moves back and forth along. So it uses its current position, which is probably 4. Like position 4 is going to be in the center of the board. 1 is on the left side. 7 is on the right side for 1 through 7 columns. We're going to drop a piece. I have a servo motor which rotates 180 degrees to like kind of knock one piece from the tube that stacks the pieces into a funnel and then into the right column. And then we move back to the center of the board with this line right here. And then if it's game over, if it detects 4 in a row, winning move inputs the board and the piece that just played. Then we start over, and we wait for a blank board before starting a new game, essentially. And let me just show you how the wait for a blank board works. Basically, we take a picture of the board and get the array, and then we say if that array is equal to a blank board, this create board function outputs a blank board. Then let's double check that, and let's take another picture. And if we get a blank board twice in a row, then we know to start a new game, essentially. And then this get board function works the same way. It waits for a change in the board, and then it confirms that change by taking another photo. And something I would like to work on to improve this function is so that it detects a new human player piece in a valid spot. So someone can't just make any change to the board. It has to be a valid change. That's a change I want to implement in the future. So that's pretty much it for this main.py. It's how it works. It goes human player turn, robot turn, human player turn, robot turn until the game ends, and then you start over with a new game. Now for this read board dot. Now for this read board script. The input of this script is an image, and the output is a 6x7 array of 0, 1s, and 2s. And we take an image right here, and then I have this debug mode, which basically shows you a picture of every single step of the process. So really briefly, overview of how this works is first we take an image, and that image can be seen. It's just like one right here. This is what the game sees, or what the script sees, and then we find all the circles in this image, which I can show you an image right here. So this is every single circle on this image is shown right here, and then we create something called a mask. We create something called a mask, which basically is like all the pixels of an image that are within a certain range of colors. So I can create a mask for all the blue pieces, and you can see each one of these little white spots represents a blue piece on the board. And if we go back here, we can see, oh, these are the blue pieces. And then from every circle, we just look at the pixels in the center, and we determine, is this a blue pixel, is it a green pixel, or is it a red pixel? And that allows me to create an array with only all the blue circles. And then from this knowledge of where the blue circles, the green circles, and the red circles are, I can take their x and y coordinates and then sort them. I sort them by their x and y coordinates, and then from there it's pretty easy to then convert it into this 6x7 array. And let me just show you some more of the code. This is just if the debug mode is on, it'll actually draw all the circles for you. This takes extra time, so normally I have debug mode turned off so that the robot takes less time to make its move. All right. And this is looking in the center. We're like, okay, is this for any given circle found? Let's check the center of it to see if there's any red pixels in it, and that's just how this works. And let me see. This right here is like a different method of detecting red, green, and blue pieces that I don't really want to get into right now. And then right here is where we sort all the circles by the Y column, and here we sort all of them by the X column, and then right here we're simply adding all of them up into a 6x7 array. And yeah, it's pretty simple to understand how it works. Writing it was a lot more challenging. I mean, just look at this. I could not get this right on the first try. And dealing with these parameters in the hue circles are very sensitive. So a lot of this was tuning the algorithm to be able to detect circles on this image. This move to pos, this controls the stepper motor, which controls which column the piece dropper is in. I use the BBIO library for this. Basically, there's a certain number of steps. So like a stepper motor works like it rotates in like fixed degrees and a fixed certain number of steps. And so here, 1740 steps corresponds to moving over one column on the board. Like that's the number of steps in between columns. So if you want to go from column 1 to column 2, you move this many steps to the right, essentially. And then all of this code here is trying to figure out like how do you smoothly accelerate the stepper motor from a starting speed to the fastest speed possible. And then this code right here is actually moving the stepper motor, and it can detect when a limit switch is pressed so that it doesn't break itself. Currently, only one of the limit switches is programmed. I have a limit switch on the other side, but I haven't programmed it yet, which actually led to me breaking the 3D printed mount I made for it, since it went off course and I couldn't stop it in time, since I hadn't programmed the limit switch yet, which just really goes to demonstrate the importance of programming in limit switches for robots, I guess. So that's the move to position, and then the position reset. So whenever the game starts, the dropper could be in like any random spot along the axis, and what this code does is from any position it moves the dropper to column 1 or column 7. Right now I have it set to move to column 1. So what it does is it moves to the left until it hits the limit switch, and then it moves. Once it hits, then it moves to the right really slowly until it's released. And this provides an accurate way to know the exact position. It's kind of like homing on a CNC machine or something. So once we know its exact position in a certain spot, then we can move a certain number of steps to the right to be exactly over column 1. So right here, we find the limit switch, we move left to find the limit switch, and then we move right until it's released, and then once we found it, then we move a certain number of steps to move over to column 1, that's right here. That just moves over to column 1. We return the number 1, which is the column it's in, I guess. Which is the column it moves over to. And then this is some code for the servo motor. This I modified from my professor Eric Welsh, and I added this part at the end, which essentially drops one piece. It's a continuous rotation servo motor, so it takes a certain amount of time to rotate the number of degrees you want to, and it's not as accurate as I would like it to be. Sometimes it doesn't rotate a full 180 degrees to drop one piece, so it'll end up not dropping a piece or dropping two pieces, which is a little bit problematic. So I'm trying to find a solution to this currently. So 0.47 seconds is basically the amount of time it takes to rotate 180 degrees. And lastly is the LCD screen, which is how the user will interact with the robot, with the LCD screen. And in the future, I'm going to add a button. The goal is to have this project be fully standalone and not reliant on being plugged into a computer. So an LCD screen provides a way to know what's happening in the game. Yeah, pretty simple stuff here. Just using this character LCD library. That's pretty much all I have to cover. Yeah.